All right, the flat plate boundary layer, kind of a classic fluid mechanics flow condition to analyze. And what we're really talking about is an infinitely thin flat plate, solid plate, that has a velocity that is uniform approaching it. And because of the no-slip condition, the fluid immediately adjacent to the boundary has to have zero velocity. As you move further away, the velocity is v0. And then this region of low velocity fluid near the boundary couples with the fluid above it to slow it down. It's through viscous action. And so as you move along the plate, oops, I wanted to do that in black. As you move along the plate, the region of low velocity grows. And so you have some transition point that increases with distance along the plate. We call that delta of x. That's the height of the boundary layer. In the boundary layer, viscous forces matter. Outside the boundary layer, they don't. Now, for the case of a laminar boundary layer, which is the only one that we did today, laminar boundary layer, we can use an analytic approach to define the actual variability of the boundary layer thickness. And it works out to be 5 times the distance along the plate. So x is the distance from the leading edge of the plate, divided by Rex to the 1/2. Rex, critical parameter in the analysis of the flat plate boundary layer, goes as V0 times the distance from the front of the plate divided by the kinematic viscosity. The shear stress along the plate, we call it tau 0, can be found from the same analytic solution and is determined to be 0.332 times the absolute viscosity, V0 divided by distance along the plate, again times Rex to the 1/2 power. And then finally the integrated force, the shear force, which is the area integral of tau, is found to be, just integrating over the area, 0.664 times the width times mu V0 REL now to the 1/2 power. And those three relationships, growth of the boundary layer, variation of the shear stress, and the magnitude of the drag force, are sort of the fundamental results that describe the interaction of the flow with this solid boundary. Now, one of the things that we'll introduce now is the idea of a coefficient of friction, which is tau 0 divided by 1/2 rho V0 squared, which for the laminar case works out to be 0.664 divided by Rex to the 1/2. And then we can think of the coefficient of friction for the force, which is Fs divided by 1/2 rho V0 squared times the width times the length of the plate, which again for the case of the laminar boundary layer is 1.33 divided by Rel to the 1/2 power. Now what we're going to do in our next lecture is think about how these coefficients of friction, coefficient of force, need to be formulated for turbulent flow. But for laminar boundary layers, this is the analytic solution.